Hello, I'm Jeremy Del Castillo and Joe Miles. We're here with Joseph Jordan. He works here at St. Peter's College on a project. He's going to tell us a little about it. So, Joe, you can go.
Okay, so my project is the micro-hollow-cathode discharge plasma microjet, and it is basically a device, like a little kind of torch that we use that generates the plasma. And what we do is we take different gases such as air, helium, oxygen, and we shoot those through the system and create plasma out of them by passing them through an electric field which is generated by the cathode and anode inside the torch itself at the tip. And from there we analyze the plasma that is created with a spectrometer, and we basically take the whole spectrum of light and try to see what we can get out of it, such as what different molecules and elements are make up the plasma itself.
Alright, cool. So what have you accomplished so far?
So far we have done a series of spectroscopy tests, such as with 98% and 2%, well, 98% helium and 2% oxygen, and see what we can get out of that. It's what makes that up, which is basically nitrogen, some oxygen atoms, and helium, and maybe some OH. But we've also done air, and we've analyzed that. We've also tried to test it in water, which we've also done, and we've done many tests regarding the plasma and that. We still need to refine them, but we've got a pretty basic understanding of how the plasma works, and we're still trying to learn more. We've taken many spectra in air so far, and we basically know the spectrum of 98% helium and 2% oxygen and air, and we're just basically trying to get to know the system, how it works, what it does, and what in the future we can get out of the plasma.
Alright, cool. Thanks for your time. Alright, see you.
Thanks. Jeremy? Okay.
Hello, this is Joe Miles, and this is Jeremy Del Castillo, and we'll be interviewing Nick and Anthony about their project today. So the first question I'd like to ask you is, what is your project called?
The name of the project is capillary DVD, which is dielectric barrier discharge.
And what have you accomplished so far?
Well, we have 4 major goals, which
4 major goals are to record IV and wavelength using a oscilloscope, have a sealed chamber, use a spectrometer, and use the displacement of microplasma and plasma current.
Well, we're almost done with the vacuum chamber, the sealed chamber. We recorded the IV characteristics using the oscilloscope. We've used the spectrometer, and we have yet to record the displacement current.
Alright, cool. Thanks, guys.
Alright.
Hello, today we're here with Carlos, and we'll be asking him a little bit about his project. So the first thing I want to ask is, what is your project called?
It's called cathode boundary layer discharge, CBLD.
And how do you exactly make your plasma for this project?
Well, we let in xenon gas inside the chamber, and then we turn on the power supply, and then little by little give it current, and then the plasma is created between it's limited to its cathode boundary layer, so it's limited to a certain area in the circle, and that's where it's limited to.
Right, so what are your objectives?
To look at the cathode modification, which is basically what the cathode goes through inside the chamber before and after it goes into it. For example, what effects does plasma have on the material, the cathode material. The other objective is to upgrade the system, whereas I'm able to turn the window around and take a picture with the camera that's already inside, the VUV, which is what we're doing now. And that's pretty much it.
And so what have you accomplished so far?
I've managed to pretty much accomplish all of that, but I'm unable to explain what exactly is going on inside the chamber when the cathode is modified, if it's the current that is affecting it or the plasma itself. But I pretty much managed to get self-organization as well. So.
Alright, thanks.
Yeah.
Hello, today we're going to be interviewing Quincy to find out a little bit about his project. So the first question I have for you is, what is your project called?
Well, it's called homogeneous dielectric barrier discharge. It refers to the plasma that we're creating inside the little Pyrex chamber that you guys have seen already. And pretty much what my goal is to use the, I don't know if you guys saw the blue spectrometer, to use that to measure the vacuum ultraviolet emissions of the plasma, the homogeneous dielectric barrier discharge, or we call it DBD for short. But there's a little bit of a problem the way the chamber is designed and the spectrometer is designed. They have to be pressed together, but they can't currently be pressed together. So what we're doing, we're in the process of redesigning the chamber so they can be pressed together and we can minimize or even eliminate the air absorption so we can get proper readings. So for right now, what I'm doing is I'm using the calibration lamps to not only to calibrate the machine, but to also gather up some data as to where the spectrometer is and make sure everything is working fine. So when we do the experiment, which can only last maybe a couple minutes, everything's we're ready to go, whatnot. So that's pretty much it in a nutshell.
Right. So what progress have you made so far?
I mean, so far we've just made sure. We've made sure that everything's working fine. There was an issue earlier where the voltage that was left on by accident, so we just had to make sure that the PMT, the photomultiplier tube, was still working. Everything's working. Like I said, we're just in the middle of calibrating the machine, making sure it still works. So there are graphs, there's data, but it's not the data that we're really looking for. What we're really looking for is when we can create the plasma, we can measure it. The air absorption is virtually none there, and then we could measure it today if we wanted to, but it wouldn't be what we're looking for, So once we get the chamber redesigned, we'll be able to get exactly what we're looking for.
Okay. Thanks.
No problem.
Alright, thanks. Alright, we're here with John, and he works here at St. Peter's College, and he's going to tell us a little about his project. So, what's your project called?
What we're working with is homogeneous dielectric barrier discharge, HDBD. And before I was working with LAS, laser absorption spectroscopy, but since getting the laser was proven to be a very tedious task, we have not actually accomplished that, and the laser will cost probably a lot of money, from $30,000 to $1 million. So we've decided to change our objective completely from laser absorption spectroscopy to measuring the plasma current via current and voltage, and vary the frequency so we can investigate its properties.
So how's your plasma actually created?
The plasma is created from a series of devices that's already in the laboratory setup. What we would do, we would turn on the vacuum pump, and then from there we would proceed to go to the nitrogen gas tank, since that's the gas that we're using for our system. We would turn on the valves, and then we would turn the flow meter on. We turn on the oscilloscope, the function generator, and the outlet so we can generate the fan for the microplasma. And then the last thing that we would do is we would turn on the DC voltage power supply, and then we would crank it up to 4.5 kilovolts, which is probably around 1.9 milliamperes, and we have plasma.
So, what are your main objectives for this project?
Well, for my sole project, my objective is to basically measure the plasma current via the frequency, and we would have our graphs will basically say, all right, here's the current, here's the time in microseconds, and here's the voltage on the other side. We're going to graph that, current versus voltage, and we're going to investigate where are the peaks, where does it decrease, increase, and whatnot, and how it behaves.
Alright, cool, thanks, John.
You're welcome.
Alright, we're here with Danny, and he's working here at St. Peter's College. So, what's your project called?
Light intensity light power, measurements of homogeneous dielectric barrier discharge.
So, what are your objectives?
At the end, to see if the plasma light, if it's just one single band of light, or it's just electrons or the light moving really fast that it looks like just one single band. What I'm told to do is find the voltage and the current and divide it, and to see if it's different wavelengths. So we see, okay, if it's one single line, okay, it's one single light like that, one solid line, or if it's just light flashing really fast at 400 nanoseconds. It's just, when you break it down, it's like, okay, light blinking back and forth, and it just looks solid.
Alright, so what have you accomplished so far?
Right now, I'm plotting the points. The photometer measures the light intensity, how strong it is, and the radometer is like the reading energy, how much light it throws out, the power. And all I have to do, I have the current and the displacement current. Displacement current is the current passing through the plasma without me being there. So all I have to do is divide the current and the voltage, and just graph and see like the wavelengths.
Alright, cool, thanks.
That's it? Okay.
Yeah.
Thank you.
Hello, I'm Angelica, and we're here. She's working here at St. Peter's College, and we're going to ask her a few questions about her project. So, what do you do in your project?
Well, my project deals with researching analytical equipment such as HPLC, mass spectrometry, gas chromatography, etc. And I'm looking at how they can be used to analyze plasma and its components. That's basically it. And what else do you want me to tell you?
So, what have you accomplished so far?
Well, I've already talked to certain sales representatives to look at how much the equipment would cost itself. I've also researched and presented on how the equipment works and operates. And recently, I've just been reading journal articles, reading how if there are any limitations to the instruments and how they can be used in a microplasma lab. And that's it.
Alright, thanks.
Thanks. That was great. Great interview. Peace out.
Good job.